Thanks everyone for being here today. I know we usually have these kind of events in person, but obviously with COVID related issues, everything seems to be online these days. So hopefully everything transitions smoothly, but please leave any questions or comments that you have in the chat. Those of us that aren't actually sharing our screens will be monitoring that and being able to provide information as the tutorial goes on. So briefly, this kind of peer-to-peer tutorial is focused on hands-on introduction to UMD's high-performance computing resources for hopefully the high-performance researcher. And so first, we're just going to have a brief overview of who we are. So we have Junaid, who is a graduate student in the Neuroscience and Cognitive Science program. Philip, who is from the Biophysics department. Me, Daniel, I'm part of the Neuroscience and Cognitive Science program, and Desanzi, who is in the Electrical and Computer Engineering program. So today's outline, we're first going to give you a brief overview of high-performance computing and what it's useful for using in terms of your research and other outside applications. Then we'll give you an opportunity to go into a breakout session where you can kind of discuss with other people here doing the peer-to-peer tutorial and discuss how it might apply for your specific research topics. Then we'll do a brief overview of the conceptual basis of parallelizing your code, which is a key component to implementing these high-performance computing clusters, and we'll give you some examples. Then we'll talk about what parallel resources are available on campus and how you can get access to them. And then we'll do a breakout session based off of your interest in your departments and have a discussion with one of the four of us with how you can get access to those resources. And then finally, Junaid is going to do a job submitting and data retrieval section where he's going to go through how to implement this code based off of the job scheduling stuff or job scheduling software that's used by UMD's high performance computing clusters. And we'll do a brief discussion of that. And then finally, we'll kind of stick around for any questions that you might have. So with that being said, first, what is a supercomputer? So generally, when we think supercomputers, we're not thinking of this. We're thinking of something more along the lines of this. In general, a supercomputer is a high-performance computing cluster. It's also referred to as a cluster or clustered computing or grid or process server. And in general, you can think of it as a collection of computing resources that are working together. So generally speaking, it's kind of like having a bunch of computers that are working on different components of whatever task or process you might want to perform. So some important terminology that we'll kind of bring up throughout the talk is first, a node, which you can just think of a single computing unit that is generally comprised of a CPU or a RAM. So, your computer might have a single node or it may have 1 to 4 nodes. It's, like I said, a single computer. Different nodes can have different specs. And then we have the head node, which is where you and everyone else logs into a high performance computing cluster. And from that head node, you then submit jobs to the multiple nodes that are part of this high performance computing cluster. So the master node decides which node jobs are submitted to. It's a shared resource, so we'll get into this a little bit later, but you don't actually run the jobs on that head node. And what a job is essentially just a single process or script of programs that you want to run on a node. So it could be a simple algorithm or analysis script that you just generally use for your analysis, for your research. So this can be also comprised of sub-processes that you can then distribute into individual nodes. And in most cases, you want to make sure that these jobs and these sub-processes are independent and don't necessarily interact with each other, so you can kind of parallelize them. And this is just kind of a brief schematic of what it looks like to interface with a supercomputer. So essentially, you use your client's SSH into the public network. You have the head node where you'll log into, and then from that head node, you can then submit jobs to the many compute nodes that are on that supercomputer. So just some general background. I think it's always kind of interesting to show what the original supercomputers look like. And now, iPhone 5S is actually pretty outdated at this point, but even the iPhone 5S has over 1,000 times more processing power than the original supercomputers that we had. So things have come a long way. And today's supercomputers often have tens, if not hundreds of thousands of processors and nodes that are capable of processing individual jobs. So this kind of processing power has come a long way, and it's allowed researchers to utilize these tools to answer questions that you couldn't necessarily answer previously. So it's kind of exciting. So what can these supercomputers be used for? They are used in a lot of computationally intensive tasks, such as weather forecasting, finance, climate research, oil and gas exploration, physics simulations, and that's just kind of to name a few areas of research that they're used for. But in general, not only do you see these high performance computing clusters used for research, but you also see them used in businesses. And therefore, it's kind of a good skill to know how to use these resources if you want to go and work on computationally related tasks for any of these bigger firms. So this is just an example of how I specifically use high performance computing clusters. I do a lot of neuroimaging work. I like to look at bigger data sets with over 100 subjects. Most of these brain images often require a lot of memory space, and the processing for even a single subject can take, a day or more to run. So essentially, if I had maybe 100 participants and I wanted to run them on one computer or my home computer, and I wanted to kind of run them in order, it would take me months for me to essentially process all these. However, with supercomputers, what you can do is you could potentially, or how I incorporate it, I submit multiple subjects, so 30 to 60 subjects at a time, and essentially you can process 30 to 60 subjects in a single day. So therefore, instead of months, it only takes you a matter of days to perform that type of processing. So now we're going to briefly go into our first breakout session, where we're going to talk about what type of processing steps and independent tasks you might be able to use or incorporate with a supercomputer that are based in your research. And if you can't really think of necessarily specific tasks that relate to your research, you can also think of just general tasks that might be used. We're going to go into a little bit more detail after this breakout session on specific implementations, but we really just want you all to get together with some of the other people that are a part of this tutorial and discuss your research as well as how you might envision implementing some supercomputing resources. So Daniel, do you want to set up the breakout sessions?
Yeah, the rooms are ready. So do people have instructions all good to go?
Yeah, pretty much. It's only going to be for 5 minutes, and we're going to just ask that you introduce yourself to the other people in the group and briefly provide a example, either based off your research or research or tasks in general, where you think you could potentially incorporate supercomputing.
All right, I'm about to open them.
Yep.
Okay.
I think you're muted.
Okay, you can see the screen, right? Yeah. Okay. So having a basic understanding on what is supercomputing and its importance. So let's look into the basics in utilizing supercomputers. So the main goal in supercomputing is to increase the task efficiency, and it can be achieved by executing tasks across multiple processors simultaneously. So think of your computer and imagine it has only one processor. So these processors are nothing like our human brains. So to complete a task, it has to focus on one thing at a time. and then move on to the next task sequentially. So let's say your computer takes an hour to complete this one problem. So now suppose that you are using a supercomputer which has 3 processors or CPUs, and if this problem is divisible or parallelizable among the 3 processors, we can think that this problem might take less than 10 to 20 minutes to complete this problem. So in real world computing, how can we achieve this sort of parallelism? So for that, let's get basic understanding on parallelization. So there are 2 types of parallelisms, task parallelism or the data parallelism. In task parallelism, individual tasks are partitioned among the processors. So each processor performs different set of tasks. On the other hand, in data parallelism, it partitions the data among the processors so that each processor performs the same task but on different set of data. So for this, let's think of an example to understand this. Think you are an instructor for a course and there are like 150 students registered for the class. So it's very a big class. And for the end exam, you include 6 questions in the exam paper. So now you have to grade these exam papers. So luckily, since this is a big class, you are given 3 teaching assistants. So how can you grade these exam papers efficiently or quickly? So, so you can allocate this task, like either you can ask each TA to mark different set of questions. For example, you can ask TA1 to mark first question 1 and 2, and TA2 to mark question 3 and 4, and TA3 to mark question 5 and 6. So in this case, each TA happens to go through all the 150 papers, but they mark different set of questions. So that's a simple example of task parallelization. Or else you can ask each TA to go through mark all the questions, but this time you allocate divide the papers among the 3 TAs. So you can allocate 50 papers to TA1, 50 papers to TA2, or 50 papers to TA3. But this time the papers do not overlap among the 3 TAs, but they do the same task. So that's a simple example of the task parallelization and data parallelization. So the parallelization is not always straightforward, and it often introduces new set of potential problems. So in generally, every task is not parallelizable. So first, we have to check whether the task is parallelizable. So in order to parallelize a task, the order of execution must not matter. So in other words, the tasks should be independent of each other. So in this case, the dependencies are the primary inhibitors of parallelization. So here, if the task 1 and task 2 are parallelizable, we can run them in 2 simultaneous processes, and the order of processing does not matter. So now let's walk through some example on dependency analysis. So here you see 2 coding statements that you find in your codes. So let's see whether these 2 statements are independent or whether they can run simultaneously. So the first statement is A equals 10 and B equals 1. So there's no dependency among the 2 statements. So in this case, these 2 statements, so the 2 tasks can run independently. Another example, so here A equals 10, B equals A. So there's dependency among the 2 statements. So you cannot run the second statement before the first statement. So in this case, the 2 tasks cannot run independently. So in general, the parallelization is done within loops. So let's walk through some examples related to the for loops. So in this for loop, we can check whether the tasks within the for loop are parallelizable, or whether they can run simultaneously, or else whether the individual iterations can run independently. So these 2 statements are simply similar to what we saw earlier. So let's check whether these two statements are independent. So here A equals 5 times I, B equals I minus 1. There's no dependency among the two statements. So these two statements can run independently. And then looking into the individual iterations, for example, iteration for the iteration I equals 0 and I equals 1, there's no dependency on the current value to the previous value. So in this case, both iterations and the tasks within the loop can run independently. Another simple example. So again, let's check whether the tasks within the for loop are independent. The current value of A depends on the previous value of A. The current value of B is I minus 1. So if you look into the two statements, there's no dependency among the two statements. So the tasks within the loop can run independently. But if we consider the individual iterations, we see that the current value of A depends on the previous value of A. So in this case, tasks can run independently, but the iterations cannot run independently. One more example. So in this case, again, let's check whether the tasks can run independently. A equals 5 times I, B equals the previous value of A. So in this case, the B depends on the variable A and also the previous value of A. So in this case, both the iterations and tasks within the loop cannot run independently. Now let's look into some more challenging tasks. So in this case, let's check whether the two individual for loops can run independently. So similarly, as earlier, let's check whether the individual iterations for individual for loops can run independently. So in this case, there's just one task within the for loop. So we need not to check the tasks within the for loop, and individual iterations, there's no dependency among the iterations. So this for loop can run independently. And for the second for loop, again, there's no dependency among the previous or current values. So again, it can run independently. And comparing the two for loops, in the first for loop, it computes the variable A, and in the second for loop, it computes variable B, and there's no dependency. So that these two for loops can run independently. So next, let's look into the nested for loops. So it has an inner loop and an outer loop. So in this case, we can check whether the inner loop and outer loop can run independently. So this sort of nested for loop can map into a grid where the inner loop can be mapped into individual rows and the outer loop can be mapped into individual columns. So in this case, we see that the value of this box is the same as the value of this box. So in that case, it depends on the rows and columns. So this nested loop, the both outer and inner loops are dependent on each other. So one last example, again, it's a nested for loop, and similarly, we can map it into a grid. So it says that the current value of A depends on the previous, is the 3 times the value of its upper box. So in this case, it depends on the individual rows, but there's no dependency among the columns. So in this case, inner loop is dependent, but the outer loop is independent. So now we know how to do the dependency analysis. So if the code has at least some independent part, we can do parallelization. So however, all the codes are not parallelizable, and does that mean we cannot run it parallelly? No, the solution is the synchronization. So the synchronization is used to enforce dependencies, and it manages and controls the ordering of events on different processes. So there are a different set of keywords that you have to mention, including your code, to enforce the synchronization. So if you look into this figure, you see that even though the task 1 completes in one processor, it does not move to the next task until the task 2 is completed. So in this way, we can manage the serialization, still running things in parallel. So this is the basics in the parallelization. And now I'll hand the floor to Philip to go through the parallel computing resources available at UMD.
So now that you guys have gotten an overview of the basics of, what parallel computing is and how parallel computing works, I want to take you guys through what resources are available to you all as researchers here at UMD. Next slide. So I'm going to be going through the most available clusters on campus. There are more beyond what I'm going to be talking about, but those are like very niche and only available to a very limited subset of researchers. So here's a brief overview before I go into them more individually. So we have Deep Thought, Blue Crab, Vswift, and Juggernaut. And on the right, you can see sort of like broadly who can access these and how many nodes there are, which is a rough approximation of how powerful they are. Next slide. So I want to start with Deep Thought 2. Deep Thought 2 is UMD's main high performance cluster, and it's really designed to be good at as many tasks as possible. It doesn't have too many like weak points in terms of, oh, it has a lot of this, but not a lot of that. No, you have a lot of cores. There's a lot of RAM per node. There's even some GPU computing capability if you have a model that supports that. And the access on this is basically if you're in CMNS or engineering, or even have a collaborator in CMNS or engineering, this computer is available to you if you go through your contacts there. The way to get access to this computer is mainly to email either your department contact or your collaborator contact and talk to them about it. There are ways to get allocations if you can't contact any of these people independently, but it's a much more involved process, and I'll be going through it a little bit later. But if possible, definitely email one of these contacts first. One of the things to note about Deep Thought 2 is that its processors are Intel 3rd generation processors. I think we're on 12th generation now, so they're a little bit older. But given that there's 488 nodes with 20 cores per node, as long as your models are reasonably parallelizable, as Dushyanthy just went through what the requirements for that are. As long as your models are reasonably parallelizable, they'll run pretty quickly on Deep Thought. Next slide. So the most powerful cluster available to UMD researchers is Blue Crab, which is a joint Hopkins UMD cluster. Now, I didn't start with this, even though it is more powerful than Deep Thought, because the accessibility is very restricted in that you have to apply for time on it. You can't just go through your department contact and they'll toss you some time on the cluster. There's a very formal application process here. However, if you do get access to it, it's good at everything. It has almost double the cores of Deep Thought, which is already a pretty powerful supercomputer. It has more GPU computing capability, newer processors, more memory per node in some cases. Now, to go a little bit into that formal application process, which applies to Deep Thought as well if you can't get access through your department contact. Next slide. We're going to go through the service unit application process here. So later when we go into breakout groups, we can guide you guys on how to actually get to this form. But basically, when you go to try to apply for time, you'll be presented with a form just like this. You'll have to state what research you're doing, what computer you want to use. And the first section here that I'm highlighting here in blue is an overview of what you're doing and what you think you need. So by what you think you need, I mean like how much RAM do you need? How many cores do you think you need? When they say KSU at the bottom, you can see it says requested KSU. KSU is kilo service units. A service unit is like one CPU hour, if that makes sense. So when you're first applying here for these service units, if you want to use Blue Crab or once again Deep Thought, if you can't get department access, you really have to have your problem set in mind. Now, if you aren't quite sure if supercomputing is right for you, but for some reason the problem you're thinking of needs to be on the scale of Blue Crab, then they do allow for what are called development units. You can get access to a small amount of cycles to sort of prototype your problem and see if it runs well in the context that you think it's going to. So see if your math scales well, and see if you can actually access as many cores as you think you're going to. But by the time you get to the point of filling out these allocation requests, generally speaking, you should be at least somewhat confident that your code requires high performance scientific computing, requires something at the scale of Deep Thought or Blue Crab, and is at least reasonably debugged, because debugging your code after it's on these clusters is a non-trivial problem. Next slide. So an important part of these applications as well is to provide a quantitative justification for the service units that you're requesting. So you're going to actually have to go through and say, okay, by doing some math, I know that my code's going to take this amount of time if I had this amount of cores. And so if I have this amount of service units, it'll shorten that to a much shorter amount of time. But you actually do have to include some basic math and what you expect to see if things seem to be working. And that's that latter part that I said there, that should be under the scientific milestones. So like, what are the results you hope to accomplish at each requested time on the supercomputer? Next slide. So another supercomputer available to the behavioral sciences and social sciences department is Vswift. Vswift is accessed through the Office of Academic Computing Services. So in this case, if you're in Vsauce, you don't need some sort of separate department contact to go email and beg for access to the supercomputers. You should have direct access through the Office of Academic Computing Services. Vswift is a much smaller cluster than either Deep Thought or Blue Crab, but it's still reasonably powerful in the sense of it has 40 nodes, a total of 560 cores, 48 gigs of RAM per core. So for large data sets, if you just need to crunch through them, and you're taking days and days and days to do it at home, this is a good place to crunch through those data sets if you have access to it. Now, if your models or your analyses require GPU computing, this doesn't really have any GPU computing capability, unfortunately. So if that's the case, you're going to have to go back to Deep Thought or Blue Crab, or the next one I'm going to talk about. Next slide. So the last cluster that I want to go through is called Juggernaut. Juggernaut is UMD's newest cluster, and it's designed as sort of the prototype for Deep Thought 3. They're testing a lot of stuff on it, but it is open for access to the same set of people that have access to Deep Thought. It actually grew out of the demand for Deep Thought being too high. So it's a smaller cluster because, like I said, it's sort of a prototype, but it's a very high performance in that its individual nodes are much newer, much fancier, much higher RAM. I mean, the amount of RAM per node in some of these nodes is up to 1.5 terabytes of RAM per node, which is pretty crazy. And although there's only 6 GPUs in the cluster, they're also very new and very high performance. So if your task requires a lot of shared memory, but doesn't require hundreds of nodes, then Juggernaut is really an appropriate cluster for that sort of task. And all of these slides will be posted online afterward. And when we do the breakout session at the end of this slide deck, we're going to be going through who and how to email and who to contact for each of these clusters. So these department references will be there online afterward, and we'll walk you through them just now in the breakout session we're going to be heading into. Next slide. So yeah, we're going to set up breakout rooms here. I went through each of these clusters as like an overview, but please join the breakout room associated with the cluster that you think is most appropriate for your research. And if you're interested, we can walk you through who to contact, how to contact them, and what further requirements are needed to get access to some of these really high performance clusters.
Go ahead and get started, because usually the stuff that I'm covering, I take about an hour and a half to cover all this stuff. Trying to do it in half an hour. So just want to, for anybody that never used one, just want to give you a little bit of a background or like a little bit of a tutorial on how to get started on using a supercomputing cluster. So I'll just go over how to access the network, launching a terminal, connecting to the computing cluster and copying files. And then I'm just going to do 2 back-to-back presentations. If you have questions, if you don't mind just throwing them in the chat for right now, and I'll try to get to them during the little break in between because we're a little tight on time.
We can also try to respond to them too in the
What's
chat.
that?
We can try to respond to them too in the chat.
Yeah, exactly.
Feel free to submit stuff.
Yeah, so the first thing, I'm assuming a lot of people already know about this since we've all been having to work from home, is that you have access to the university networks using a VPN. If you're wanting to use any of the high performance computing clusters, you have to actually use the VPN because they're only on the university networks. And so you have to VPN onto the network. And this is basically just a virtual private network that allows you to kind of get on the university network and act as if you're on campus, and that way you can connect to anything that's connected to the university network. If you don't have it set up, here are links to where you can go and download the software and get that set up. Then next, I have to say, if you're not really used to using terminals, I think using some of the university supercomputers might be a little bit more of a challenge because you have to kind of interface with it using the terminal. This is the command line. It's like a non-graphical interface to use your computer. Macs have it pre-installed, and you can find it in the utilities folder in your applications. Windows, I think newer versions, I think Daniel was saying that newer versions have the command prompt with like bash and stuff set up. But I think older versions of Windows, you have to sometimes use some sort of third-party application to be able to use a. And in my previous job, I did use MOBA Exterm because they were very Windows centric. And finally, for a Linux person, then this part is all really easy for you. So to get to connect to your server, you have to shell in using the terminal, and the command for that is SSH. And the syntax is basically use your university ID at and the server address. Whenever you get an account on one of the supercomputing clusters, they'll tell you what the login URL is. And this is basically how you shell in. And this will ask you to provide your password. It's using the university password authenticator, so you don't have to like set up a new one. It's the same one that you're using for emails and everything. And once you do that, you're voila on the head node of the computing cluster. And this is where you can kind of run basic commands and look at the different files you have on. But as Daniel said in the first tutorial, you do not want to run big jobs on this, because then it'll make it so that nobody else will be able to access the server. And you probably will get an email from the administrator saying, hey, what are you doing? So this is what it looks like. I recently had to, my stepson is getting into Linux, and he was like trying to shell in. He's like, I don't understand. I'm typing my password and the cursor's not moving. So just more of like, just to give you a heads up, like when you're typing in your password, the cursor doesn't move. For a lot of people doing research, you're probably going to want to move some of your own files onto the server that you're going to be using. So really basic bash command is called SCP, or secure copy, and it works very similar to, if you've done any sort of bash programming, it's very similar to the copy command, in that you want to give it first the path to from where you want to copy the file, and then give it the path to where you want the file to copy to. And in the case of like copying onto a server, you're going to use the same sort of syntax you did as when shelling in. So you'll give it username at server address : then the path where on the server you want to have it copied to. So this is a specific example. If I had like a text file saying I heart HPCs, I could copy it that way. And then vice versa, if you want to pull this stuff down from the server, like run a bunch of analyses that wrote to files and you want to look at them locally, you'd go in reverse order. And finally, if you have like a folder of stuff that you want to move over, you can use the -R option, which is recursive, and then you can move an entire folder's worth of stuff. There's more information here. This is one place where you can use some sort of a graphical interface. FileZilla, it's a little bit glitchy, but it works if you're wanting to move a bunch of stuff. All right, so Slurm, this is the job scheduling software that is used by all of the university supercomputing clusters. There's a variety of different job scheduling software, and they all kind of work the same, but they each have their own different syntax. So I'm going to go over this. I'm just going to introduce this right now before I move on to the really in the weeds how to use this kind of stuff. So Slurm is just a simple Linux utility for resource management. Basically what it does, it's a workload manager. So if you submit some sort of computationally intense process to the server, it's figuring out like what nodes are open, what kind of specifications you need. So if you need like 24 gigs of RAM and you need it for 30 hours or whatever, it like kind of equitably divides up the computational computing resources amongst the different users at the server at any time. And then you're basically going to be, the Slurm is going to be running with whatever sort of applications you're using, which I'll go into in a lot more detail in a second. I like this schematic because it kind of explains how job scheduling works. If you're, you can kind of think of the job scheduler as the host of a restaurant. So you have a line of people that are all wanting to eat something or process data, and the job of the host is basically to figure out like what is the appropriate size table, or what is the appropriate RAM analogy, and in cases where if you're have like a wanting something really heavy duty, like you need multiple nodes with like Philip was talking about 1.5 terabytes of RAM, then you can submit that job and it might wait a while, but it will kind of reserve that space for you and do it in order of when the jobs were submitted. And so, again, just to give you some ideas of like different ways that you can use it from like a lot of, I guess, people here, I do a lot of neuroimaging analysis, and these are really great resource for neuroimaging, because usually even doing data processing for one person takes a very long time, and it involves multiple steps. But using job scheduling, I could have each person's data processed on a different node. Similarly, for people that are like more physics and math, if you're doing parameter tuning on some sort of hardcore deep something, I'm kind of out of my element here, so I'm just kind of making up words. This is another great application for this, where you can submit, estimate the model performance for a range of different parameter values and have them run simultaneously, and that will kind of cut the processing time, by whatever number of nodes that you divide it up amongst. Referencing back to Shanti's presentation, though, whatever you submit to an individual node, they absolutely has to run independently. There are ways of kind of having cross-node talk, which I won't get into. The computer science department hosts a supercomputing boot camp that's 1 week long. It costs $100. That one really gets into like how to write multi-processing interface code and stuff that like makes you completely in control of how the processors are interacting with each other. I'm going to be talking at a much higher level than that. If you are wanting to kind of get more into the weeds, I think if you just look up HPC boot camp at UMD. They host it, I think, maybe twice a year. All right, and so the heart of Slurm is the sbatch command, which is how you submit a job to the cluster. Yeah, and so that's just like the command that you're using, and you use it in conjunction with whatever job script. Like, so if you're using MATLAB, you would write, some sort of code or script in MATLAB, and you would use that in conjunction with this sbatch command, which I'm going to go into much more detail in just a second. And when you're using this command, there are three things, at least on the supercomputers that I've gotten a chance to use on campus. There are three things that you absolutely have to specify: the number of nodes that you need, or alternatively, you can specify the number of cores that you want, the amount of RAM that your job will need, and the time to process the job. In general, you want to try to figure out as closely as possible how much of these resources you'd want to use, because if you aim too high, for example, you're not really sure, so you request 100 gigs of RAM. That means that you might have to wait a little bit longer, because those, it's a finite set of resources, and the way the job scheduling works, it puts you in order. Going back to the diner example, if you're a party of 20 people, you might have to wait a little bit. So if you can kind of estimate the resources you need to as closely as you can to the job that you're going to run, you're more likely to kind of have your job start running sooner than later. And there's a lot of other things that you can specify, and there's Slurm and sbatch in particular just has pages and pages and pages. If you Google search it, there's lots and lots of documentation on it. Yeah, and the super basic usage is sbatch, and you can specify the options after the command, and then whatever job script it is that you want to run. In just a second, I'll show you that you can actually have the options specified within the job script, which I think is a little bit more preferable and easier to kind of reproduce. And then once you do that, it gives you the job number, which allows you to kind of check in on how the did the job actually start running? Is it still going? Did it crash or whatever? All right. So any questions so far? Because it's about to rev up really quickly in terms of complications. If there's something I didn't quite explain well enough. Let's see the chat. Sorry.
I have one question.
Mm-hmm.
Yeah, so you said before, distributing to the your assigned number of cores. You said that you'd recommend running a small job on the head node first.
No. Well, I mean, if you can do very basic things on the head node.
Okay.
If you are wanting to test stuff, and again, just because there's so many different things to cover, I didn't really include this, but maybe I'll upload another slide deck that I've used in the past. There you can get onto a compute node interactively, and the command for that is sinteractive.
I see.
And that's a good way to kind of test around and figure out how the code, for benchmarking, that kind of stuff. Then once you figure that out and you want to use that piece of code on multiple nodes, that's when you then do the job submission. But yeah, that's a very good question, because testing it on your local computer will not necessarily give you the proper estimates that you would need to specify for the supercomputer.
Thanks.
All right, so I'm just gonna keep on moving. All right, so now I'm gonna go into how to write and submit code with examples in MATLAB and R, but this is really generalizable to Python and many other languages as well. So the basic approach, the different Slurm options that you can specify, are really just the couple of favorites I have, and I'll go into specific examples. So the easiest way to do this really is to write a standalone piece of code. If you're working in MATLAB or R or Python, write some piece of code, you can kind of test it using an interactive node. And then you can create a wrapper script for it. And what the wrapper is basically just telling the shell, to launch a compute node and run whatever script that it is that you just wrote. And I'll explain a little bit in a second when we go into the MATLAB example why you have to, or why this is a more general purpose, easier approach, because you can use it for nearly every programming language. So yeah, the wrapper function contains the syntax and options that are specific for Slurm. And it can give instructions that are specific to the programming language that you're using. Really important considerations when you're writing code for a supercomputer. It has to be able to be run non-interactively. So once you submit your, super fancy simulation in Python, it is now on a compute node that you cannot interact with. So, whatever code you write, you have to make sure you've tested it in advance before submitting it. Yeah, so that just means you can't do anything to it once it starts. You can have it set up so that it's taking input values, or if you have like files that are being processed by your code, you can have that specified when you're submitting, but once it's submitted, you can't really do anything. If anybody wants to go start working on deep thought and report back, I may be wrong about this, but from my understanding, you can't really launch any graphics, nor can you render graphics, but that might not be the case, especially with Juggernaut and some of these others that have like these big GPU nodes. And then, yeah, the other big thing is again, this kind of goes back to the idea of like non-interactive, like your code, if there's like a solution that you're trying to get to, you want it to have like write the code so that it would at least print the solution to a screen or save to a file. Like for example, in MATLAB, we can, or like some of the loops that Vishanti was kind of using as examples, we could have a variable be populated over multiple iterations of a loop. But if that variable is still in MATLAB world, once your process node ends, it disappears. But if you have it print to the screen, then you'll be able to see the solution in the output log that you get. Okay, so what goes into one of these job scripts? So the first thing in these job scripts is a line that's called shebang, and it indicates what programming language you're going in. Bash, I feel like, is very general purpose, and this is what you can write your wrappers in. But you can also have Python or R code written like this as well. MATLAB, because it's not something that you can run directly through terminal, it's still like kind of has to launch its own stuff, requires the wrapper. And then the next set of things I have here are the different SPatch options that you have to specify. So again, the amount of time you want for your job, the number of nodes, and the amount of memory are absolutely required. If you don't include those, then when you submit your job, it will automatically stop and say, hey, you didn't specify this, that, or the other. There's a ton of options that you can add, but some of my favorites are, I like the mail option because especially if you have something that's going to run for a long time, if you provide it your university email address, it will send you an email once it actually starts running and once it finishes. And if it's like something like a simulation that you expect to take a couple of days and you get the email saying that it's already finished, then you probably know it crashed. So it's like a good way of not having to constantly just stay at your terminal and check in on the process. Also, you can kind of specify the output logs, otherwise it creates these output logs that are all named slurm, whatever the job number was, and out. This, like if you're running multiple subjects, it kind of helps you keep track of that. So like in the example of neuroimaging, if you're, had like 30 subjects you're wanting to run, having the output logs named by the subject ID will make it easier so you know which one would have crashed rather than having to like go back and figure out what job number was assigned to it and everything. And then, yeah, after you, in the code that you write, after all the Slurm options, then the rest of it is basically what you want your code to do. As a reminder, again, I feel like I've said this over and over, and I did just update Philip's slides. I pulled it last night when they weren't completed. But everything that we presented today, including examples that I won't even get into, but that will allow you to kind of take this even further, is on this GitHub repository. All right. From my understanding, there are a lot of MATLAB users. And MATLAB is like a very special case in which you absolutely have to use a wrapper, unless, I don't know if there's, somebody might be able to correct me if I'm wrong about that, but I've never been able to use it without one. And so the general sort of workflow for running MATLAB jobs on one of these supercomputers is write your standalone MATLAB script as you would on a local workstation or using one of the interactive nodes. You can copy it up to the server, or if you've written it in the through your terminal, then it's already there. And then you write a wrapper script to submit it, which I'll go into in just a second. This is just a Monte Carlo simulation of coin tosses that I just grabbed from MATLAB Central, just as an example. It takes a little while to run, but it kind of meets the qualifications in that it provides the solution in the command window once it's done running. Yeah. So, okay, so we have this MATLAB Monte Carlo simulation code, and we want to run it on our computing server. So we have to write a MATLAB wrapper. In this case, this is a specific wrapper just for this piece of code. And what this contains, again, you have all the Slurm options, as I just talked about. And then one of the first things you want to do is load the MATLAB software. So all the university servers have like a centralized software system, but they're not all preloaded. So you can actually even specify if there's something about MATLAB 2020 that you like. You can say, hey, I want to use MATLAB 2020, and you can, all of this works through the module load command, which if you go to this URL, it gives you sort of over the top ad nauseum details about how to use that. And somebody had asked how responsive the people are in terms of adding new software, and they seem to be pretty good. Again, since University of Maryland is such a big research university, they want to kind of stay ahead of the curve and are always updating stuff. And the beautiful and easy, great thing about that is that it makes it so that you personally don't have to install software, and especially if it's a software that requires all these different dependencies and stuff, they figure all that out for you. And then, yeah, so you load MATLAB, and then you want to launch MATLAB with no desktop, no display option. Otherwise, it will try to render graphics and crash. And yeah, it will give you kind of an error message. And then I never knew about this option in MATLAB until I started using supercomputers, is that you can use the -R option, and everything that comes after the -R, you put in quotes. This is what would run after MATLAB has launched. So this is like you launch MATLAB and then you type in these commands into the MATLAB window. And that's how you can use like a bash wrapper to run a MATLAB script. And in this case, like I said, this isn't the best wrapper because it is completely specific to that Monte Carlo simulation code that I just showed you. But I do have examples of how to make a more general purpose one. So you could use this wrapper script, but say, I want to run this other piece of MATLAB. I have an example, which is example 2 on the, yeah, it's MATLAB example 2. It's just a more general wrapper. And then I also have examples if you have like a MATLAB function that requires input, how to set up a wrapper for that, as well as probably the most important thing, which unfortunately, because so much to cover, I won't be able to really get into, is how to set up an array wrapper. So for example, in the case of a parameter tuning problem, you have a range of parameter values like 1 to 100, you can set up an array, which would be just one of the options that you set up here, and say, I want to run this code for all these values. And that automatically kind of parallelizes it for you. And the cool thing about that is, it will kind of divide up the computational resources equitably among different people that might also be doing that. So you don't, ideally, you won't have to worry about somebody using up all the nodes, although on Vswift, sometimes it doesn't work out that way. So does that make sense? I know I'm trying to like really rush through this, but the need for a wrapper in MATLAB. And this, again, you can use this same approach. Oh, nice. Yeah, you can use the same approach to run any software in any language. But the cool thing with, oh yeah, sorry. Let me finish this. Yeah, so to run this, because this wrapper has exactly the script that you're wanting to run hard-coded into it, then in this case, all you have to do is sbatch, and then this will submit to one of the compute nodes, and it will give you a job ID number, which then you can use to track later. And then once you, so in that example, I had the output log called MATLAB example1.log, and you can use the more command within the terminal then to see what happened. And so basically it's exactly like it's what would print to the terminal if you were running this locally. So it's launching MATLAB, and then it outputs the solutions to this Monte Carlo simulation. Oops. But the great thing is, unless if you're not a MATLAB user, which I've been trying to get further and further away from, is that a lot of other programming languages have their own sort of internal environmental stuff set up so that you can kind of use them as you would a wrapper script. So in this R example, oh crap, this is a typo. I did not mean to leave that in there. Ignore that. In this R example, you can just set up the shebang for an R script and then submit it just as is, as long as you give it the proper Slurm options. So this is a set of standalone R commands that are kind of meaningless, but just wanted to kind of have an example. Then you set up the, I'll edit this and update the repository. I apologize for that. But this is the actual R script shebang you would use. And then for this, you could submit it by itself using the sbatch command. And you can kind of check the output using the more command like I mentioned before. And same thing with Python. This is the Python shebang that you would use. Man, I did that again. Sorry, did this kind of late last night. Got a little sloppy. But yeah, like I said, that was like a really quick dash through all the stuff. There's a lot more of the resources on the GitHub repo, including other examples of how to do this for MATLAB that I did not have time to go over. Oh yeah, always do this shameless self-promotion. I've been using supercomputers for a while and happy to set people up, but at this point I'm trying to graduate and super busy and poor. So maybe I might ask you for a beer if you need some help. I was hoping to have like at least 5 minutes for question and answers. Unfortunately, looks like we're almost at time.